Hey everybody, Paul here again. Last video for the week. I wanted to look really quickly at another kind of graph that you've maybe seen before, mentioned briefly, but we haven't been explicit about, and it's called a digraph. Here, right here, here's a graph where the letter represents a student, so student A, student B, student F, student C, and the edge represents has had a class with. So A has had a class with B and E. And the idea of this kind of edge is that if A has had a class with B, then by definition, B has had a class with A. So the edge connects them, but it doesn't really matter like what you think of as the starting edge or the ending edge or whatever, because it's just the edge. Um, Not all relationships can be modeled with this exact kind of graph. Here's an example of one. What if you wanted to represent a situation, right, where each of these letters represents a student, but the edge represents is older than? A normal edge won't work. Like, is A older than B or is B older than A? We don't know because in this graph it doesn't make sense. So in this graph, we're not going to use a normal edge like this. We're going to use like an arrow. And so what we're saying is A is older than B. And actually A, we can see from, based on this information over here, right, the orders of the ages, A is actually older than D as well. And A is older than E because A is the oldest. And we can see that E is also older than D, right? And F is older than B, F is older than C, F is older than D. You can see how this gets a little bit messy right now. But every single one of these edges is actually going to have an arrow on it. And this is not a normal graph because a normal graph has edges that don't have arrows. This is called a digraph. So I want to go through a few of the basics of how digraphs work, right? So a digraph is a graph with directed edges. That's where the die part comes from. Die is short for directed. And it's used when a relationship, right, represented by an edge, does not imply connection in both directions. So older than only goes one way. It's not connected like has a class with. So here's an example, right? Five friends decide who is the best at the card game War. Now, just to be clear, War is not a game. There's no choices to make. You can't be good at War. Doesn't matter. Whatever. Every player plays each other player exactly once. A vertex represents a player, and an edge with an arrow represents beats this player. So we can see from over here, right, that when 1 and 2 played, 2 beat 1 because the arrow points from 2 to 1. So this means, right, this means that 2 beat 1. Okay? So this is a digraph, and just like a normal graph, we can talk about this and we can talk about its vertex set and its edge set and all that kind of stuff. Let's see what this looks like, right? So find the vertex set, find the edge set, and the degrees, and notice there's a plural here, the degrees of each vertex. Okay? The vertex set is the exact same thing as normal. It's just the 5 vertices listed. Now the edge set, let's look at what we have here. So in the edge set, we have, so we have 1, 3, 1, 4, 1, 5. Notice we do not say 1, 2. Why do you think we don't say 1, 2? Tick tock, tick tock. Yes, you're absolutely correct. Thank you for raising your hand. We don't say 1, 2 because the starting vertex is going to come before the ending vertex in our edge. So we don't have 1, 2. Instead, we have 2, 1. Right? So even though 1 appears 4 times in this edge set, because there's 4 edges in total, right? We don't list it as 1, 2. We list it as 2, 1. So we would not use 1, 2 in this. We use 2, 1 instead. Sorry if I'm being super repetitive, but I want to make sure you understand. And then the last thing is when we do the degrees, it's going to be a little bit different. Not sure why this looks like that. Our degrees, right, are now ordered pairs. Any thoughts on what the two different numbers stand for, right? I'll give you like 1 second to look. So there's our numbers, right? There's our graph. In fact, I'll move this graph down here for us right now so we can really see it nice and clearly. There's our graph. Here's our degrees. So if we look at 1, right, 1 has a single degree coming in, and it has 3 edges going out. And 1 is 1 comma 3. So what this is, right, when we do this, it's actually what we call the in degree and the out degree. So 1 is 1, 3, 1, 3. 2 is 0, 4 because there's no degrees going in and all the edges are going out. We can see 3 is 2, 2, 4 is 3, 1, and 5 is 4, 0, right? So 5 has all 4 edges pointing in and 0 edges pointing out. Okay, so it's the same idea. And notice as you add these numbers up, you get the normal degree. So if we're doing degrees in this, we're going to go ahead and say what the 2 are. But if we add them, we would get 4 for all these because there's 4, degree 4 for all those vertices there. Okay. Digraphs can also have walks and paths and circuits, just like regular graphs. I would push you, if you don't know what walks, paths, and circuits are, check out the notes that we've posted from previous stuff, okay? They're still on Classroom. You should still have them in your notebook, right? This says, find a path of length 5. Okay, so length 5. So it's going to actually matter, I think, where we start. I think we're going to have to be a little bit more careful than we were before. For example, if we started at B, and we started here, and we have to go to A, and then if we went down to D and over to, that's a length of 4. But now we're stuck. So unlike when we did normal graphs, you really have to be even more thoughtful where we start. I think to find a path of length 5, I think we want to start at A. So we're going to go A to D. And then we're actually going to go up to B. So that's 2, 3, 4, 5. That's our 5, right? I can show you again real fast. Here's 1, 2, 3, 4, 5. So our path of length 5 would be A to D to B to A to C to B. Remember, 5 is counting the edges in between. And remember also, it's okay that we repeated B and A because we didn't repeat the edge, we just repeated the vertex. Find circuits of length 3 and 4. Go ahead, pause the video, think for a minute, okay? How would you find circuits of length 3 and 4 in this graph? While you're thinking, I'll go ahead and I'll erase some of these things. Oh, not going to work that way. Right? So, circuit of length 3, we kind of want to find like a triangle. Oh, here's a triangle, right? So here's a circuit of length 3. Boop, that works. So we could do B, A, C, B. And then to find a circuit of length 4, I think in this case we can actually just go around. 1, 2, 3, 4. So that would be A, D, C, B, A. Okay? So the only difference between a digraph and a regular graph is in a digraph the edges are directed. You can't go in either direction. You can only go in one. I hope that makes sense. Please feel free to reach out if you have any questions. Try the problems that are given. They're fairly straightforward. I tried to cover all of them in this. But as always, if I messed up, my bad. I'll talk to you guys soon. See you in class. Take care. Bye-bye.